coming to our seminar where Henry is going to be talking to us about regular graphs with extremal rigidity properties.
Yeah,
Take it away.
thanks for the introduction, and thanks for all coming. So this research was done this spring at Budapest Masters of Mathematics, where I studied abroad last semester, and it was with my collaborators Kaylee Weatherspoon, Zayu Zhang, and our mentor, Dr. Tibor Yudon. So first, we got a picture of us on the last day. We were in Budapest. I think every single one of these pictures was not very good, but one of us was bad, and I chose the one that was bad. But yeah, so Zay on the left, Dr. Tibor Yudon, center left, me in center right, and Kaylee on the right. Okay, so first, I'm just going to talk about the history of rigidity in mathematical literature. So I haven't given you a definition yet, but just go for intuition for the first slide. So in 1776, Euler first conjectured that all polyhedrons are rigid, and later in 1813, Cauchy showed that this is true for convex polyhedra. So for our icosahedra on the left, this is rigid, there's no way to continuously deform the shape. Although there are examples of concave polyhedra that are not rigid. I've made this out of paper before, and it ever so slightly wiggles. It'd be nice to make a good example of that sometime. And you can also notice that on the icosahedron, you could take this vertex and flip it inside. And you could have a different polyhedra where all the edges are congruent and all the faces are congruent. But it's a different realization of the same graph if you look at the vertices and edges.
You mean you can flip it? You mean that you can do it continuously? Or?
Not continuously, but globally or yeah.
There is another one which this one is for.
Yeah, exactly. So if you're only given the information about the vertices, positions, or the lengths of the edges, then there could be multiple realizations. Okay, so first I'm going to talk about a d-dimensional framework, and this is just a graph and an embedding into RD. And we say that a framework is rigid if there exists an epsilon, and such that for any other framework of the same graph, where the edge lengths are the same, and the distance between the vertices does not change very much, less than epsilon, then the distances between non-edges are also preserved. Okay. And similarly, we define global rigidity to be this idea of the icosahedron, where if we just preserve the distances between edges, then we also get that the distances between non-edges, the distance between two vertices that don't have an edge, are maintained. Okay, I can come back to this slide if we need. Yeah. Okay, so let's just have a few examples. I guess we can just look at the bottom first. So the square is not rigid. That's kind of easy to see. You've played with little Tinker Toys before. And then on the second and the fourth, we have cliques. So clearly cliques are going to be rigid and globally rigid. And globally rigid is going to imply rigidity. So the middle example is interesting. So this is an example of a rigid framework in the plane, but not globally rigid in the plane. If we're in R3, you could rotate around this edge continuously. So it would not be rigid in R3. Okay, so then for the last one, I'm going to define what it means to be generically rigid, or a framework is generic if the multiset of coordinates of the vertices is algebraically independent over Q. So this just means they're placed randomly, in arbitrary way. And you can make any generic framework generic just by moving it around because Q's dense in the reals. But here's an example on the left of a rigid framework, but it's not generically rigid. So the reason why it's rigid is because in this drawing, I have those four vertices in a line. So it's kind of like a taut string. But if this was generic, there'd be a little play on those four vertices, and it would be to wiggle a little bit. Yeah. Okay. So the first way that mathematicians attacked rigidity, or we're going to understand it, was this idea called the rigidity matrix. So first, we can define motion between two different d-dimensional frameworks of the same graph with some function p. So the 0, 1 is just going, you can think of it like time, going between the two different frameworks. And what's special about this continuous function is that it starts and ends at these two frameworks, and also the edges, the lengths of the edges is preserved throughout the motion. So that's what this equation 1 is for. So on the left, this is the length of the edges at some point t, and these are the initial lengths of the edges. Okay, so I don't know much about differential geometry, but you can assume that P is differentiable or even smooth. So differentiating 1, write out the 2 norm, you'll get this equation because this is a constant, and you can take the derivative. The denominator is a constant, and plugging in t equals 0, so the initial time at the first framework, p0, we get this equation too. I'll show it in later slides. So this needs to be true for all uv, where uv are edges. And we're going to use this to make a rigidity matrix, and I'll talk about that on the next slide. I might flip back to this slide. Okay, so the rigidity matrix of a d-dimensional framework, M of GP, is an E, where E is the number of edges, so the size of the edge set, times dv, dimension, times the number of vertices, where the entries are the ith dimension for the coordinate of P of U and V. So I think this is easiest seen in an example. So here is a 2-dimensional framework of a small graph, and I have the first vertex, second vertex, and third vertex. The first 2 coordinates, or the first 2 entries, are talking about the edges going through point 1. So I have I have x1 minus x2 for the left edge, and y1 minus y2 for also the left edge, but in the y component. And if I was in higher dimensions, I would just repeat this. In the second, I have the 2 edges coming out of point 2, and in the third, the edge coming out of x3, or point 3. So the important thing about the rigidity matrix is that the kernel of the rigidity matrix correlate to the vectors of motion of this framework. So we would have a d times v vector in the kernel is going to be a d times v vector dimension. And you notice that each, yeah, go ahead.
Should there be x on the second line instead of the y every line?
Oh yes, right here. Yes, sorry. Copying mistake. Okay, so notice that each row corresponds to an edge in the graph. So this might be much larger for larger graphs, where each row corresponds to an edge in the framework. And if you multiply any number in this vector that's in the kernel, we expect to get this equation. So an element of this vector is going to correspond to an instantaneous motion of a certain vertex in a certain coordinate, so x, y, z. Okay, so this is useful because now we're going to be able to talk about the rank of this matrix in general. Okay, so the first theorem says that the rank is at most d times n minus d plus 1 choose 2. And if equality holds, then we get the framework is rigid. Okay, so I already mentioned this first bullet point. And then what we notice is that there's a certain amount of continuous transformations or motions that preserve, that are always in the kernel no matter what the graph looks like. And these are going to be translations and rotations. Maybe there's some more complicated motion, but they're all just going to be translations and rotations. So there's going to be, the dimension of the translation is going to be d, and the dimension of the rotations is d choose 2, because you fix 2 dimensions to rotate, and or I guess you choose 2 dimensions to rotate and you fix the rest. And that adds up to d plus 1 choose 2, and the number of columns is dn, so you subtract d plus 1 choose 2. So now, if GP is not rigid, then there exists a pair of non-adjacent vertices such that we can change them slightly, towards each other or away from each other. So P is our continuous function of the motion of the vertices. So the derivative is going to be, the difference in the derivative is going to be positive. Because if the vertices are placed generically, this is why I assume them being generic, two vertices are not going to overlap, be in the same place. So that means this is going to be non-zero, and since translations and rotations preserve distances between points, the kernel must be strictly larger. We have some instantaneous motion, that's all we can think of as the vector in the kernel, which is not a translation or a rotation or combination. Okay, so this is very useful. And it's going to bring us into the main theorem in rigidity theory, specifically in the plane. So from now on, I'm going to talk about generic frameworks in the plane. I think I forgot to stress something, actually. So this proposition, I didn't say this. So this proposition says that for any two generic frameworks of the same graph, either they're both rigid or they're both not rigid. So as the talk progresses, I might just reference a graph being rigid, which I mean that any generic realization of the graph in the plane is rigid. So I'm only caring about the plane, and this is true. This proposition is true in any dimension. But this is just a nice thing, so I'm just going to reference a graph being rigid. Okay, so we have Lemann's theorem in 1970, and I'm going to recite this theorem many times in the talk, and it's very useful because we won't have to work with the rigidity matrix as much. So there's a few theorems that we use that allow us to talk about the graphs like combinatorially, so you don't have to look back at the rigidity matrix. Okay, so this says that the graph G is minimally rigid, by which I mean you can, if you remove any edge from the graph, you break rigidity. And minimally will always refer to the edge count, unless said otherwise. So it's minimally rigid if and only if we have the edge count is 2v minus 3. So if you plug this into your previous equation, you have 2 times n minus 3 choose 2. And for any induced subgraph, it's not too dense. So it has the same density parameter, so 2 times the number of vertices minus 3. This proof's involved, but I think it's worthwhile for you to see where it comes from. And we use these similar techniques when we talk about more complicated rigidity properties. So first, he uses these two graphic operations called the 0 and 1 extension. So the 0 extension just adds a vertex of degree 2. There may or may not be an edge here. And the 1 extension does the same thing, but we want to preserve the edge density of the graph. So we add a vertex of degree 3, but we must remove an edge. So there needs to be an edge induced by those 3 vertices. And by induction, you can show that these two operations preserve the rank of the matrix. It's not too difficult to show. So what he also shows is that applying a 0-1 reduction to a Lemann graph, by which I mean a graph that satisfies the conclusion, results in a Lemann graph. Sorry, so a 1 or 0 reduction is the inverse operation of a 0-1 extension, respectively. And then he just notes that, well, K2 is rigid and Lemann. So if I have any graph that is Lemann, follows this conclusion, I can reduce it down to a K2. And in this proof, that's the really hard part, is showing that you can always reduce by a 0-1 extension. And and later on, that's going to be the hardest part of these proofs. In this case, it's not too difficult. So we start with a Lemann graph, we get down to a K2, it's rigid, and then we can undo this sequence of 0 and 1 extensions, which preserve rigidity. So this graph will be rigid if it's Lemann. So the other direction, I might be able to sketch out a little bit. This more directly uses the rigidity matrix. So we prove this by contrapositive. And so let's say that there's too many edges. There's more than 2v minus 3 edges. Well, then he notes that this rigidity matrix is going to be dependent, because each of the rows in this rigidity matrix corresponds to an edge in the graph, and the rank is maximized at 2 times v minus 3. So if there's one more edge, there's one more row, and it's going to be dependent on the other edges. on the other rows, that means we can remove that row or remove the edge, and we still get a rigid graph. Okay, so that means that a graph is rigid, minimally rigid, then it must have 2v minus 3 edges. Okay, so since we're proving it by contradiction, let's suppose that the other statement is false. So that means that we have a graph G, and we have some subset of the vertices X, where the size of the edge set of G induced on X is going to be greater than 2 times X, the size of X minus 3. Okay, well, so now notice that any induced subgraph of this, I guess you would take a minimally, like a smallest counterexample X, because then you wouldn't have a subgraph of X that's going to be too dense as well, or you can assume that. And then you can look at the graph induced on X, and this is going to be a Lemon graph, or it's going to be like an overdetermined Lemon graph. So we're going to have too many edges, but it's still going to follow the later substitution. I don't think that's necessary, but I'm just giving you a proof sketch. And then what you do is, the nice idea is that we can remove an edge from this X, and it's still going to be rigid. Well, that's not going to change the rigidity of the graph as a whole, because this subgraph is still rigid. We could like replace it with a kx for size of x, just a clique. And so that's the idea of this proof. Okay. Okay, so I want to show you first one of the why Lemon's theorem is really powerful. So first, going to introduce an idea called essentially k-edge connectedness. This is very similar to just regular k-edge connectedness, although we say that if there's a edge set of size less than or equal to k, then they have to have a common incident vertex. So if I had, or another way to say it is that if there's an edge set that of size at least k, I'm just going to say, yeah. If there's an edge set of size k, let's say 4, then there has to be at least 2 vertices on each side. That's what essentially k-edge connectedness is. So
you're saying all small classes are just around single vertex.
Yeah, that's another way to say it. Okay, and this is, it seemed kind of weird at first when I saw this definition, but it relates a lot to rigidity, and that's part of Lemon's condition that I didn't stress before, is that we need the size x to be greater than or equal to 2. Because if it's 1, then that can never be true. Okay, so our first proposition is that if G is rigid, then G is essentially 3-edge connected. And this is just a counting argument. So we suppose this is false, so there's a non-trivial edge cut. So a trivial edge cut is where one of the sides has one vertex of size at most 2. Let this edge cut be of the form x, v not x. So in this picture down here. And the other key idea is we looked at a minimally rigid subgraph. This is an idea we use a lot, because if we have a rigid subgraph, then adding any edges won't change the rigidity. They won't destroy the rigidity. And then we can just apply Lemon's condition. So for H, our minimally rigid subgraph, we know the edge count is 2v minus 3, which is going to be less than or equal to the edges in each of the sets plus 2. And then we can apply Lemon's condition to each subset, and then we add and we get 2v minus 4. We get a contradiction. But also clearly that's not rigid. But it's nice that we can use the math to be able to say that's not rigid, even though it's very obvious that's not rigid, or even if there are 0 edges between there. So this is very nice. Okay, so now I'm going to start getting into the research that we did this spring, and this takes some more definitions, but they're all very similar. So I might refer to these as just redundant rigidity. So we say that G is k-vertex rigid if for every subset of vertices that is less than k, then G minus x is rigid. Or we could say with globally rigid, or edge globally rigid, little diagram. And it's supposed to say R2, but this is an old picture. Yeah, still working the plane. Okay, so we know the extremal values for, so extremal means the number of edges for one of these rigidity properties. Here's a chart of the extremal values. And so we understand one edge rigid and one vertex rigid is just rigid. And same with globally rigid. Well, I'll talk about globally rigid in a minute. So these two are well understood, and these two values are well understood. So we're going to focus on this paper is 3 edge rigid, 2 edge globally rigid, and 2 vertex globally rigid. And the other thing to note is that these all have minimum degree 4. And so that's easy to see by just looking at a single vertex. So if I have a single vertex, and I have the rest of the graph. So if it's 3 edge rigid, that means I need to, let's say it has less than 4 vertices. Then I want to be able to remove 2 edges and it still be rigid. If I remove this edge and I remove this edge, it's clearly not rigid. And we'll talk about that a little bit more. And same with 2 edge globally rigid. If I just have, if I have 3 edges and I remove one, I have a vertex of degree 2, and I can flip this along. And same with 2 vertex globally rigid. Instead of deleting the edge, I can delete the vertex. So K edge rigid is a stronger condition than K. K vertex rigid is a stronger condition than K edge rigid, if I have that right. Okay, so our target is the characterization and inductive constructions for, we use this word strongly minimal as just minimum. I like the word minimum, but I guess it sounds better to say strongly minimal. For 2 edge globally rigid and 3 edge rigid graphs, and we show their equivalence, characterization, and inductive construction. And similarly for 2 vertex rigid, we give a characterization and a conjecture on inductive construction. And lastly, we use these results to show connections to 2 vertex rigid graphs. Okay, so our first result. So if G is 4 regular, so it's at the extremal edge count, then G is essentially 6 edge connected if and only if G is 3 edge rigid. So the essentially 6 edge connected is easy to see, as we already shown that a rigid graph is essentially 3 edge connected. So if our graph is 3 edge rigid, we should remove 2 more edges and it'd still be essentially 3 edge connected. But since our graph is Eulerian, so every vertex has an even degree, every edge cut needs to be even. So we're guaranteed 5, and we get a bonus 1 for free because we're 4 regular. So that's what this proof talks about. And the forward direction, I don't know if I'm gonna have time, but if I do, I'll come back to it because it's neat. Okay, so now let's talk about global rigidity. I'm not going to go into the proof at all. It's similar to the Le Mans condition, just much more involved. So a graph is globally rigid in the plane if and only if G is either a clique on most 3 vertices, or G is 3 connected and 2 edge rigid. So we clearly need the 3 connected condition, because we could have like a KN here and a KN here and just flip one, even though they're very dense. And the 2 edge rigid gets complicated, but the idea is that it uses the same 1 extensions from before, and they inductively choose these 1 extensions from K4. The weird thing about higher redundancy rigidity properties is that you have to worry much more about being able to get back to this root graph. And sometimes you can't. And you also don't necessarily have the condition that a minimal graph has a minimum number of edges. I should put the picture, but there's a good picture for 2 vertex rigid graphs that it should have, the extremal value is 2v minus 1, but there's a graph that has 2v vertices and there's no edge that you can remove to get down to a smaller graph. Okay, so we'll use this result on the next slide. So So our next result shows the equivalency between 2 edge globally rigid graphs and 3 edge rigid graphs. Note this is only at the extremal level. So if you take this graph, it's going to be 3 edge rigid for sure, but it's not going to be globally rigid. Okay, so the forward direction is quite easy from the previous theorem. So if it's globally rigid, it's redundantly rigid, which is an old term, which is saying 2 edge rigid. So we can remove an edge, it's still rigid. Thus, it's 2 edge globally rigid. Thus it's 3 edge rigid because if we can remove an edge. Yeah, it's 2 edge globally rigid, so we can remove an edge from this condition, and then we can remove an edge from globally rigid. So then the reverse direction is nice. So we show that G is redundantly 3 connected, meaning I can remove an edge and it's still 3 connected. So our graph is, if it's redundantly 3 connected, that means there has to be a vertex cut of the size 3, right? And since it's 4 regular, our edges must look like this, like spiders across. And if they were any other way, let's say we had 1 vertex here, and maybe it looks something like 1, 3, 3, 1. So we still obey the Lamont condition. We can still get a smaller edge cut. A smaller edge cut because if you look at the edge count, we have more than 4 edges coming into here. So we need to have at least 2 vertices. So this is a non-trivial edge cut, and we would get a non-trivial edge cut of size less than 6, which would be a contradiction. Okay. Okay, so we've now characterized these graphs, 3 edge rigid and 2 edge globally rigid, as at the extremal value when they're extremal edge count when they're 4 regular. They're essentially 6 edge connected. So now we want to give an inductive construction. So an inductive construction is where we can build up these graphs from like a root graph, and at every step along the way, it has this property. And we introduce the idea of a 2 extension. So this is where we add a vertex of degree 4 to like 2 edges that are matching, or just 2 disjoint edges. And well, we're also going to have the 2 reduction, which is the inverse operation of this, and we need places to put edges, so we don't have duplicate edges. So the way that we prove this, that any of these graphs can be obtained from a K5, a series of 2 extensions, is there's actually a result in 2007 that was almost there. So it said that you can produce these graphs by a 2 extension and an additional operation that look like this. And we show that you don't actually need this operation. I think the next slide talks about it, yes. So we have our theorem still. We still have our theorem up there. So the way that the proof approach goes is it just says what would the graph look like if you have a vertex, say in red, that you can't 2 reduce? Well, its neighborhood, so we have its neighborhood. So we can't 2 reduce at it if there's no pair of disjoint edges, like a pair of pairs of vertices that are disjoint and there's no edge there. So either we can have a triangle there induced in the neighborhood, or we can have a star. But in fact, if we have a triangle, say, then these are all degree 4, we have a non-trivial 4 edge cut. So it must look like this. And in the proof given in 2007, the other operation basically just adds a K4, or basically just adds a K4. So they don't, they were taking into account this scenario, but this scenario is impossible because it needs to be essentially 6 edge connected. So it's just a simpler inductive construction. Okay, so done a lot of math, let's do some examples. So a nice class of examples we call C and K, where we take a cycle on n vertices and then add the kth neighbors. So it's a little bit different from the power of a cycle. So we still have 4 regular graphs. And these are examples of, I haven't talked about 2 vertex globally rigid graphs, but these are examples of all 3. And when K is equal to 2 and 3, it's easy to construct sequences of 2 extensions. It was much harder to prove. You actually used some like algebraic graph theory to show in general. It's one of the results that we knew it was true. We just needed something else to prove. Okay. Okay, so just to recap. So we've shown that these 4 conditions are equivalent for 4 regular graphs. And now let's talk about 2 vertex globally rigid graphs. Okay, so it turns out the conditions for 2 vertex globally rigid graphs is very similar, but we also need the graphs to be 4 connected along with essentially 6 edge connected. And this proof is now actually pretty simple. I think I just give a sketch here. So it's a quick contrapositive, and it's a similar counting argument from the Lemons theorem that we've done before, where you look at an edge cut, and you can say a little bit more about the edge cut because now we need 4 vertices. For sake of time, I won't go into it. And the forward direction is also pretty simple at this point. But it uses properties of 2 edge rigid graphs. So 2 edge rigid graphs and 2 vertex rigid graphs were studied a lot before we started, and we can use a lot of those results. You can look at an induced subgraph that is 2 edge rigid and say certain things. It just gets more complicated because it's really easy to talk about a minimally rigid subgraph, but it gets more technical when you have redundantly rigid subgraphs. Okay, so we've given our characterization here. What about an inductive construction? So it seems that the 2 extension works for regular, essentially 6 edge connected graphs. I bounce between calling it 2 vertex rigid graphs and at this. Although there is a special graph, namely the K44, that doesn't allow you to get back to a root graph. So on the next slide, I have a tree to make a little more sense. So the root graph is K5, which has all 3 of these properties that I'm talking about. And if we apply 2 extensions, we get this tree. There's just 2, these graphs are isomorphic. There's just 2 different arcs. But we get this tree. And all of these graphs are 4 connected except for this graph. So this is our favorite graph in our research because it's the smallest, essentially 6 edge connected, 4 regular, essentially 6 edge connected graph that is not 4 connected, if I said that right. 4 regular, essentially 6. Yeah.
It's K6 minus, no, it's 7.
So,
it's 7.
yeah, it's K7 minus a square and minus a triangle. Yeah, so this was our favorite graph. And if you notice, and this is extensive to 8 vertices, if you notice K44 can only go back to, can only be reduced by the 2 extension to our favorite graph. But our favorite graph is not 4 regular, 4 connected, but K44 is. And I think there's actually an arrow here, but K44 is the counterexample, and that's why we have to state our conjecture at 9 vertices. So our dream is that we can say that every 2 vertex rigid, globally rigid graph can be attained from K5 or K44 via 2 extensions, but we haven't proven this yet. And this is just the hard thing we have to say, because you need to know some global knowledge of the whole graph to be able to say that there exists some 2 extension at some vertex that will result, if you reduce, you'll get a 4 connected graph. Yeah. Okay, so lastly, we're going to use our results to connect to previous research done by Brigitte Cervasis in '89. And so she first introduced the idea of redundant rigidity, but she released a paper in '89 on 2 vertex rigid graphs. and these have an extremal value of 2v minus 1 edges. And at the end, she had an inductive construction, specifically the 1 extension. But the problem is you can't just choose any one reduction from your graph. You have to be really careful. And you need global knowledge to know where you choose this 1 extension, the 1 reduction from. So what we show is that there's a relationship between the essentially, or the 3 edge rigid graphs and the 2 vertex rigid graphs. And this is by either one of 2 graph operations. The first one is just an edge deletion between 2 vertices of degree 4. So I haven't talked too much, I'll write it down, about 2 vertex rigid graphs yet. But their extremal value is 2v minus 1. So it's just 1 edge away from our 4 regular graphs. And you can show that the minimum degree is 3, and that means that either of these graphs are going to have 2 vertices of degree 3 not adjacent, or 2 vertices of degree 3 adjacent. So this can be a 4 regular graph except for one of these 2 scenarios. I won't go into the proof, but or her proof. This is what the 2 graphs look like, and either they can be obtained from a 3 edge rigid graph by edge deletion, or from a vertex splitting operation, depending which case we are in for the 2 vertex rigid graphs. Okay, so what's useful about this is we know how to inductively construct our 3 edge rigid graphs. So if we want to more easily construct let's say we want to determine if a 2 vertex rigid graph is 2 vertex rigid, then we can first check if it's one of these 2 scenarios, apply the inverse operation, so adding an edge or edge contraction, and then now we have a good test, and a very efficient test, if the graph is 3 edge rigid, just by applying 2 reductions. And if we get at K5, then we're done. And one of the last things we did in our paper was we showed that you can do this more directly. You can actually just apply the 2 extensions directly to 2 vertex rigid graphs. They somehow just act independently of these vertex splitting. You have to be a little careful, but you only need to have some local knowledge about where these vertices are. You need to be applying the operation like right here, somehow on the graph. And so that is a proper, what I'm talking about is going to be a proper inductive construction, because at every step along the way we have 2 vertex rigid graphs. So the reason why it's an improvement is because we don't need to have global knowledge of the graph to apply this reduction to a smaller graph. And I believe that's it. Yeah. So yeah, any questions?
Yeah.
So, yeah.
If you go to slide 6.
Yeah.
Why can you assume that V is differentiable?
I don't know too much about differential geometry, but
Alright.
they just say that in the paper as well.
Okay.
If you know something about differential geometry, you can assume it's smooth, even. Yeah.
Alright.
Sure.
Yeah, so I wanted to ask, so all your work is focusing on 4 regular graphs.
Yeah.
So I wanted to ask how hard would it be to do more than that?
Yeah.
Consider other graphs.
Yeah, I think that's the next direction of research. So actually this summer, Robin Huang went to Budapest for the summer for the RU program and worked on 2V plus, or on 3 vertex rigid graphs. And that sort of finishes off all the graphs that are only off by a few edges on their density. So all these graphs are related because we can apply these little graph operations between them. But all of a sudden we get to significantly more dense graphs because we need them to be 5, 6 regular. We looked at it a little bit, but it's just significantly different. I'm optimistic that it won't be too much harder, but my professor tells me it's hard. So, yeah. You can also do this for higher dimensions. It's completely understood in one dimension. Almost all of the extremal values are known in 3 dimensions, and some, but yeah.
So is 3 dimensions significantly easier, I guess?
No, it's significantly harder. There's, I forget, it was earlier in the semester, but somewhere around here, there's a gap of 1 and like a gap of 17.
Huh.
But what I don't understand yet is, if you look far ahead, they can understand it completely in 3 dimensions. That was some previous semester's work. So either you can try to narrow down those extremal values, or you can start working on these characterizations and inductive constructions for the 3-dimensional rigidity properties that we understand the extremal value of. But yeah, we just focus on the plane. Yeah.
It seems as though if you're not globally rigid,
Mm-hmm.
but are locally rigid, say, then I can boost my dimension by a little bit.
Yes.
And I won't be locally rigid, that I can find a smooth motion.
Yeah, it's actually always 1 dimension.
So it's, okay, I was
Yeah.
gonna ask the smallest dimension, okay.
Yes.
So it's just always, I just need one more dimension to realize a smooth motion.
Exactly.
Okay.
It's kind of surprising because it could be complicated.
Yeah, I was expecting possibly needing more,
Yeah.
but just one is enough. Okay,
Yeah, that's a
cool.
good question.
Cool.
Any other questions? Awesome, well, thank you, Henry, really nice talk.
Yeah.